Hi everyone. So for this section, we'll be going over resonance of benzenes and just essentially showing how resonance plays out in electrophilic aromatic substitutions and nucleophilic aromatic substitutions. Okay. And so before we go over that, let's first practice some resonance with electron donating groups and electron withdrawing groups. Okay. And so let's first start off with this aromatic ring with an OCH3 on it. Okay, and so the first thing you want to note is the fact that there are lone pairs on this OCH3, and because of those lone pairs which are conjugated to this benzene ring, we can call this an electron donating group. Okay, and so with this electron donating group, you can really see that once we do the resonance structures for this molecule. So to start off resonance, we'll take these lone pairs and notice since they're conjugated, right, these lone pairs can donate or be shuttled into the ring, okay? And so we're going to draw the double bond onto this carbon-oxygen bond, and this double bond on the ring is going to be pushed, essentially, to the carbon on the ring. And so you get a negative charge on that carbon. We get a positive charge on this oxygen because of the 3 bonds, okay? And so this is the first resonance structure. And so from here, this negative charge can be pushed into the double bond right here, and that double bond will be pushed off onto this carbon right here, and we get a negative charge on our resonance structure on that carbon. Okay, and so before we go any further, I just wanted to point out, right, the positions on this ring. So this is the ortho, this is the meta, and then the para, okay? And so in the first structure, the negative charge lands on the ortho position, okay? In the second structure, the negative charge lands on the para position, okay? And so in our last resonance structure, we can move these negative charges onto the bond right next to it, and this pushes that double bond onto the second ortho position. So the negative charge will be here. Let's draw out all the double bonds. And so notice that the negative charge is now on the ortho position. Okay, and so in terms of the last arrows we can draw, we can put these negative charges back onto the bond and then neutralize that oxygen to go back to our original molecule. Okay, and so those are the resonance structures. And so the key thing to note, right, is that through the resonance structures, we were only able to get a negative charge on the ortho position, the para position, and then so both ortho positions and both para position and the one para position, okay? And so before we go over the consequences for that, let's go on to electron withdrawing groups, okay? And so looking at the molecule below, right, with this carbonyl, this is considered an electron withdrawing group. And that's because of the double bond right here, which is conjugated with this ring right here. And because of that double bond, we're actually able to shuttle electrons away from the ring into the oxygen. And so let's look at what that looks like essentially. So first, we're going to take these electrons in the double bond, and then we can shuttle them to the oxygen, okay? And these electrons right here will be pushed out of the ring in order to essentially follow the electrons that are being pushed into the oxygen. And so the resulting resonance structure would look something like this. So we have a negative charge on our oxygen. We form a double bond right here, and then draw our double bonds out. And since the double bond is pushed away from the ring, we generate a positive charge on the orthocarbon. Okay. And so now we can continue pushing double bonds and shifting it around the ring in order to get different resonance structures. And so we can take this double bond, push it towards the positive charge, and we get another resonance structure. And so in this case, the positive charge is now on the para position. And then in our last structure, we can shuffle the positive charge one more time. Okay. And so we end up with the positive charge on the second ortho position. Okay. All right. And then just to finish this off, we can push the electrons back onto that carbonyl and then neutralize this molecule and neutralize that positive charge. And we go back to our original molecule. Okay. And so now to contrast essentially the chemical consequences, right? We can look at first this electron donating group, right? And so in this case, the ortho and the para positions in the resonance structure, they had a negative charge. And so we can say that the ortho and the para position are considered partial negative. And so the ortho and the para will be the, or are the most negative positions on the ring. Okay. And so now let's look at our electron withdrawing group. Okay. So for the electron withdrawing group, our ortho and our para positions were positive in the resonance structures. Therefore, the ortho and para positions are partial positive. Okay. And so comparatively, right, if we want to look at what's most negative, if we compare the meta position with the ortho and para position, right, the meta position is neutral. Okay. And because these meta positions are neutral, whereas the ortho and para positions are partial positive, we can say that the meta position are the most negative. Positions on the ring. Okay. So when you have an electron withdrawing group, the meta positions are where most negative, whereas when you have an electron donating group, the ortho and para positions are what are the most negative. Okay. And so when we try to apply that to electrophilic aromatic substitution, right? Remember that in SEER, the ring is the nucleophile, okay? And so if the ring is the nucleophile, we want the ring to be the most negative, because remember that good nucleophiles have negative charge, or partial negative charge at the least, right? And so when we look at the ring right here, okay, right? So this ring right here, okay. We have an electron donating group, right? So we have an EDG, and therefore the ortho position and the para position are considered the most negative sites on this ring, okay? And so given, let's say we have an electrophile right here, so this nitronium ion is our electrophile, we can either attack with the ortho position, or we can attack with the para position, okay? And so, as a result, let's look at the para position. If the para position is the one that attacks, okay, following this arrow, we get the major product, which is the major product where the NO2 is added at the para position because it's the para position that attacks the nitronium ion. Whereas if the ortho position is the site that attacks the nitronium ion, we get the minor product where the NO2 is on the ortho position, okay? And so just keep in mind that this is the major product because there is less steric hindrance at the para position, okay? And so with electrophilic aromatic substitution, right, when we have an electron donating group, we are going to add our electrophile to either the para position, which is the major product, or the ortho position, which is the minor product. In the case of an electron withdrawing group, okay, so with this carbonyl right here, we establish this is an electron withdrawing group. Remember, it's the meta position that is the most negative on this ring. And because it's the most negative, this is the position that will attack our electrophile, which in this case is the nitronium ion still. And so the product we end up with is the NO2 group, the nitro group, being added to the meta position. Okay? And so overall, electron withdrawing groups and electron donating groups, they contribute resonance to this ring, right? And so for electrophilic aromatic substitution, resonance will determine site selectivity. Okay, and so this is essentially where to add on the ring. Okay, and so let's contrast that with nucleophilic aromatic substitution. Okay, and so in nucleophilic aromatic substitution, the ring is the electrophile. Okay. And so since this is the electrophile, right, we want it to be more positive, okay? And so given a nuke, right, the nucleophile will attack the area with a leaving group, okay? And so this is the main difference between electrophilic aromatic substitution and nucleophilic aromatic substitution, in the sense that for SNAR, which is nucleophilic aromatic substitution, we need a leaving group on the ring. Okay. And so in this sense, the electron withdrawing groups and electron donating groups are not determining where we're adding the nucleophile onto the ring, and more they're just stabilizing the charge, which I advise you to look back on Michaela's video on electrophilic versus nucleophilic aromatic substitution mechanisms, and really understanding the fact that for SNAR, the resonance is not affecting where you're adding. It's again, it's stabilizing the positive charge or the negative charge when the nucleophile attacks. Okay. So again, resonance doesn't determine site selectivity. Instead, it stabilizes the negative charge when the nucleophile attacks. Okay. And so those are the main differences in terms of resonance, at least, between SEER and SNAR. Okay. And so that should be the end of this section.